Okay, let's do this. All right, today we have arcs of circles. We're going to talk about arcs. We know a little bit about arcs already. We know what an arc looks like. But today we're really going to define what an arc is and the properties that arcs, central angles, and chords share together. So first of all, an arc, okay? An arc, it's red, this guy right here. This is an arc. And an arc is defined as it consists of points on a circle, and all the points on the circle needed to connect the points in a single path. Now, what am I talking about? You have these 2 points here, A, and you have B. When you connect A and B going along the circumference of the circle, you have created an arc. It's basically a piece of the circumference, a fraction of the circumference. And that's what an arc is. Okay? Now, when you have radii AO and OB, they connect. They determine the central angle AOB, and AOB is intercepted by arc AB. You with me? Okay. As far as the arc center is concerned, so we just talked about AOB, that is the center of an arc is the center of the circle of which the arc is part. So you have circle O here. This is the central angle. It's also the angle that is intercepting this arc. So that is the arc center. And the central angle, of course, is an angle whose vertex is at the center of the circle. So again, when you connect AO and BO, not only do you form a central angle, but that central angle is also the arc center, and the chord opposite that arc center, it's called as being intercepted. That is the intercepted arc, and that's what you get. Yes, sir? Yes, arc center would be called AOB, just like the central angle. Okay. Now, why the differentiation? Well, sometimes we're just talking about the central angle. For example, if I wanted to find the length of AB, there's a formula for that. If you guys remember, it's the central angle divided by 360, right, times the perimeter, because it is a fraction of the perimeter. So in that case, I'd just be using the central angle. If I say the arc center is 46 degrees, you just have to know that the arc center is the same as the central angle. But they could go by both names. It's circumference, which is the perimeter of a circle. And no, it is not diameter. It's 2 pi r, or diameter times pi. Either way. Thank you. Does that make sense? All right. Let's continue. All right. Now, let's look at how to name arcs and find the difference between a minor arc and a major arc. Okay? If you look here, you got AB here. This is my arc, AB. Now, that is called a minor arc. It is called a minor arc because it is less than 180 degrees. It says here that the measure of the minor arc is less than 180 degrees and includes all points on or between the sides of the central angle. So this is very important. Not only can you tell that is less than 180 degrees, because 180 degrees would be right there, the diameter. Okay, so that's less than 180 degrees, but also what's important is this part right here. It includes all points on or between the sides of the central angle. If you look at this central angle here, these are the sides of the central angle, correct? The arc includes all points in between these sides. So it makes sense. I know you guys understand that, but so you could put definitions to actual figures. Okay, hopefully it makes more sense. Yes, sir. Okay, the question was, how do you know that arc AB doesn't include the other half? I'm going to tell you that right now, my man, because that's called the major arc. Great question, son. Give me 2 seconds. So let's still stick with the minor arc. In this particular case, The minor arc is AB. And as you can see, it's written AB. You just write AB and you make a little arc symbol. Okay? So that is the minor arc. Now, let's get rid of all of this for a second. All right. We have our center here still. Okay. Now, the major arc. The major arc is different. The measure of the major arc is 360 degrees minus the minor arc. And it includes all points on or outside of the central angle. Let's remember that this right here, AOB, is the central angle. Everything within it is the minor arc. But everything outside of it is the major arc. Okay? So how would you name that though, Mr. Moore? You're still going from AB to AB. Okay, excellent. Someone said it. The major arc here would be written as ACB. You could also write it as arc BCA. But when you're talking about a major arc, you're going to include 3 points. And that's how you can tell the difference between AB and ACB or BCA. Does that make sense? Yes, sir, and yes, sir. The question is, will there ever be a time when they don't give us the third point? Not often, but if they did, you would not be able to name the major arc. You would just be able to name the minor arc, which would be AB. So if they did that to you, you wouldn't really be able to determine the name of the major arc. But you would be able to determine the measure of the major arc. If I told you that AB was 60, and I didn't give you the C, and I just said find the measure of the major arc measure would be 360 minus 60, very good, which would be 300 degrees. But I wouldn't be able to name it, again, if I didn't have that C point. Does that make sense, son? Yes, sir? Okay. Yes, sir? The question was, can't you just call it major arc AB? No. No, sir, unfortunately. Good question, good thinking. Very good thinking, but you're going to have 3 points. Yes, sir. Yes, sir. Okay, what if there's a point between the A and the B? So, for example, if there's a point, oh, that's not going to show up too well. Let's say there's a point here, and let's call that D. Well, then you have different things here. You've got arc AD, arc DB, or or AB. You wouldn't say ADB. You only include the third point with a major arc. Okay? So again, you'd have AD, you'd have DB, or you have AB, or BA. Because it's a minor arc, so it does not matter that you have that in the middle. You need that third point for the major arc. Yes? You have a question? Okay. Does that make sense? Everybody?
Yes.
Awesome. Good, good, good. Okay, so let's continue. Let's just do a real quick example here. Find the major arc. In this case, we can name the major arc. Yes, sir. That's exactly right. So arc ACB would equal 320 degrees. Why? Because the major arc is 360 minus the minor arc of 40, and that's 320. Does that make sense? Awesome. Okay, now, let's talk about semicircles real quick. A semicircle is defined as an arc whose endpoints are the endpoints of the diameter. We know already the degree measure of a straight angle. So what would this the measure of this line B here, let's call this AB. It'd be 180, very good. So arc AB would equal 180, very good. Now in this case, you have arc AB going this way, and you could have arc AB going this way. In this particular case, it does not matter because they are congruent. And with that, we're going to lead into congruent arcs and the difference between measures and actual values, okay? So, let's look at what I have here. I got this circle within a circle. Whenever you have two circles that share the same center, it's called concentric. So when I have congruent arcs, okay, let's talk about congruent arcs. Two arcs that have the same measure are not necessarily congruent arcs. Does anyone remember the difference between the measure of an arc and the length of an arc? What is the difference there? When I ask you for arc measure, what am I looking for? And when I ask you for arc length, what am I looking for? What am I looking for here? Yes. Thank you. Thank you, son. Arc measure is in degrees. It's degrees, okay? And we're going to go over, again, the central angle theorem and the inscribed angle theorem and the exterior angle theorem in the next slide. But the measure, we're talking about degrees. Yes? And the arc length, yes, the question was, don't you need a value for the radii? Well, absolutely. But I wanted to know if you guys knew what this was. The question was, what is arc length, not do you need a value for the radii? That was not the question. The question was, what is arc length? Okay, now they're asking me about similar arcs. I don't want that. What is the arc length? Okay, very good, son. Arc length is a distance. Very good. And there is a specific formula for this arc length, this distance. It is central angle over 360 times circumference, which is 2 pi r. So please know the difference, or of course diameter pi, yes. Please know the difference between arc measure and arc length. Now let's go back to the congruent arcs. In order for arcs to be congruent, and in order for anything to be congruent, you have to have the same degree measures and you have to have the same length. So in this particular case, okay, I tell you that the measure of arc AB is 65. Of course it is. That's true because the central angle is 65. Of course. I tell you that the measure of CD is 65. Of course it is because the central angle is 65. But AB and CD are not congruent. Why? Sir. Thank you, thank you, thank you. The answer is because CD has a different radii than CA, or OA, I'm sorry. OC is different than OA. In this particular case, OC is smaller. Okay? So the circles have different radii. So that means that they cannot be congruent. So what must happen? What do you think has to happen in order for arcs to be congruent? Yes, sir?
The same circle.
Very good. In order for arcs to be congruent, the main gist here is that the circles must have congruent radii. And we already know that if circles have congruent radii, then those circles are congruent. That's exactly right. So what's happening here? If I have arcs in the same circle with the same arc measure, then they're going to be congruent. If I have arcs from two congruent circles, two different congruent circles with the same arc measure, then they're going to have the same arc length as well, and they're going to be congruent because they share the same radii. Does that make sense? Everybody? Okay. So now, an example of what I just said. Two arcs are congruent whenever they have the same measure. We're talking about degrees and are part of the same circle or congruent circle. So in this particular case right here, arc AB would be congruent to arc CD. Why? Because they have the same angle measure and they're part of the same circle, so that means they have the same radii. They're sharing the same radii. Yes? So then very good. I just had a question that said, so then would that make AC congruent to BD? Absolutely 100%. Well done, son. And let's think about why. If this is 60 and this is 60, okay, and these two are congruent, how many degrees are left in this circle? 240 degrees. Exactly, 240. So if this has to be congruent to that, then that would be 120 and that would be 120. Does that make sense? Yes? Okay, the question was, could the arc be placed in different, of course, in different parts. If I have this circle, and I tell you that this arc AB is, whatever, 75 degrees. But then I say that arc BC is also 75 degrees. What are the criteria here, my man? Do they have the same measure? Do they share the same radii? So then they are congruent. They do not have to be across from each other. I just made that drawing across from each other so you could vividly see it. But they could be right next to each other just like you see here. Does that make sense? Yes?
How would you put CD to the left and therefore arc AC would not be to prove that AC was congruent to BD?
Okay. The question here was, I'm a little bit confused. You're confusing me. You're confusing me. Come up, please. Go ahead and do your best and explain it to me because I have no idea what you're saying.
We have two arcs. Say
Okay.
A.
So he's drawing two arcs. Arc AB and CD. Okay. Perfect. That's what I had before.
That's 70.
Let's say arc CD is 70
70.
and arc AB is 70. Yes, sir. Okay, so that's 140. So that there means that there is 220 degrees left. Yes, sir.
But then how do you know that these two are congruent?
Okay, how do you know that those two are congruent? Because you have no choice.
Yes, we do.
Yes, sir. Yes. I know you don't. You have no choice.
Wouldn't this be 70? This thing right here? Wouldn't that be 70 because it's central?
Exactly. Thank you.
And this would be 70. So this is congruent to that because of supplemental congruent angles.
Very good.
All right.
That is fantastic. Thank you. That is fantastic. The question was, let me go ahead and make that clear because that was a very valid question and that was a very valid answer. I'm very proud of you guys. The question was specifically this. You have an arc here and you have an arc here and you say that this arc is 75, let's just say, and this arc is 75. If that arc is 75, that means that the arc angle is 75. If this arc is 75, that means that that arc angle is 75. Then supplementary angles must equal 180. So there is absolutely no choice but for that to be 105. Then you have vertical angles are congruent, or again, that's a supplementary angle, so that must be 105. Okay, so there is, hold up. There, in this case, I am 100% guaranteed correct here. This would be 105, and this would be 105. You're not assuming anything. You're not assuming anything. You have radii here. That has to be 75 degrees, correct? Correct? Everyone, you right? This has to be 75 degrees, correct? If these are 70, they're both 75 degrees, that means that I have vertical angles. They will be straight lines 100%. Okay, thank you very much for your question. Okay, so now, if two arcs are congruent whenever they have the same measure and are parts of the same circle or congruent circles. So just like here, in this particular case, I can say that arc EF is congruent to arc GH. Why? Okay. If I tell you, like, let's say this is X and this is X. If I have the radii are congruent in two circles, that means that the circles are congruent. So I have arc EF with the measure of 50 degrees. I have arc GH with a measure of 50 degrees. Since they have the same radii, that means that they are congruent circles, so therefore they must have equal lengths, and therefore arc EF would be congruent to arc GH. And then I've got another fact for you, and you guys may want to think about it before you ask me questions, because I am right. If the minor arc here is 50, could I now say that the major arc of these two circles are also congruent? Absolutely, okay? And the major arcs here would equal 310 degrees. Okay? All right. Let's continue. Now, this is old stuff, so I'm going to go really fast. Central angle arc theorem. The measure of the arc is equal to the measure of the central angle, period. There is no if, and, or buts about this. If that's the central angle, x degrees, then the arc will be x degrees. Call that A, B, or whatever you want to call it. Yes, sir. The question was saying this was in a proof, we just put that. I don't know what that means, but you would say central angle arc theorem. Because the central angle arc theorem states that the measure of the central angle is equal to the measure of the arc. Inscribed angle arc theorem. The measure of the arc is twice the measure of the inscribed angle. If I said that this was 60 degrees, then that means the arc measure is 120 degrees, or vice versa. If the intercepted arc from the inscribed angle is 200, then the inscribed angle is 100. Yes?
Sounds like if it would also going down the line, see the A.
Okay, I have no idea what you're saying. You're saying that the thing will go down. I have no idea what you're talking about. Sure. I have no idea what you're talking about.
If this line kept going down like this, and then this line kept going down like this, and this could also be X.
Of course, because then there would be vertical angles. But if it was vertical angles, that drawing is wrong. That drawing is wrong. But if they told you this on the SAT or the ACT, and they said that arc was X degrees, it doesn't matter what the drawing looks like. What would the central angle be here? X would have to be. Not because the drawing says so or because Mr. Morrow says so, but because the math says so. If the arc is X degrees, that means the central angle is X degrees. If this arc is X degrees, that means that this will be X degrees. And then guess what? If these are vertical angles, that means these two are vertical angles, and these two would be 180 minus X. And that would be 180 minus X. I'm not going by the drawing, I'm going by the values. Yes?
Is it possible to have an inscribed angle, have a central angle also?
The question was, is there possible to have an inscribed angle and a central angle? Sure. Why not? Okay, if this is 120, what would the central angle be? 120. What would the inscribed angle be? 60. Yes, absolutely. The laws are the laws are the laws are the laws. Yes, sir. Okay, we're not there yet, so let's just hold on. Yes, sir.
If the semicircle is an arc whose endpoints are the endpoints of diameter, would it also be like could you also have a semicircle with an inscribed angle instead of just a central angle?
Okay, the question was, can you have a semicircle with an inscribed angle? I don't see why not. I really don't see why not. I have this circle, and I have this diameter, okay? And then I have this inscribed angle here, okay? If I tell you that arc AB equals 180, I know now for a fact that AB, segment AB is 180, and that is a semicircle. It is the diameter. Then what would the inscribed angle be? 90. Because again, the formula does not change. I don't care if you have an inscribed, a semicircle, and a central angle. The formula works the same. If I had a central angle here, like this, what would the central angle be? 180. Well, in that case, that's wrong. I can't do that. The central angle is 180. That was stupid of my part. I apologize. Okay? All right, but I could have this. How about this? I could do this. Let's say I had C and D here, and I said that this was 60. What would arc CD be? Exactly. Does that make sense? And then, well, we'll get into arc AC and BD in a little bit. There's a theorem for that. Okay? All right. Now, last one of review. Exterior angle arc theorem. The measure of the exterior angle equals half the difference of the measures of the two intercepted arcs. Okay, so that means that this angle X out here, this exterior angle, is equal to 1/2 of A minus B. So this works out a lot. You see this a lot in the ACT and the SAT and all that good stuff. And you're going to see it on the tests and the homeworks. If you had something like this, and I tell you that this was 80, and I said that this angle here was 20, and I wanted to find arc AB. How would I do that? Think about the formula. What was I given? What was I given? Okay, I was given the X, thank you. 20 degrees equals 1/2 of 80 minus arc AB. Okay, multiply by 2, you got 40 equals 80 minus AB. Subtract 80 to both sides. So that's negative 40 equals negative AB. So AB would equal 40 degrees. And that makes sense because 80 minus 40 is 40 divided by 2 is 20. It's all in the formula. Does that make sense? Okay, now I got to teach you the rest of the lesson. We have a lot more to learn today. But first, right quick, let me get one volunteer. Okay, come on up. Go ahead and just click on this right here. Okay, and just with your finger drag the first one that comes out to the appropriate spot here in the circle, please. Okay, so the major arc. Where are we putting that major arc? What's the major arc here? Okay, we're in the circle. What is that though? You can go ahead and show me. So major arc would be here. Go ahead. Let's make it fancy. Okay, now your finger is a highlighter. Show me. Ace. Okay, so great job. major arc is ACB here. Great job. Excellent. Next, come on up. Same thing, please. Go ahead and you're going to choose one. No. Okay, there you go. Minor arc. Where's the minor arc? All right. And then let's just highlight it. There you go. So, minor arc is AB. Awesome. Next, come on up. Very good point. Very good point. Let me make this a little bit darker here. Okay, the question was, can there be two minor arcs? I know that there's minor arc AB, but couldn't you also have had minor arc AC? The answer is yes. And you also, yeah, CB, we don't know that, yeah. Very good. Excellent. Good job, son. Next. Okay, what's the chord here? And the chord is AB, absolutely right here. AB is the chord. Awesome. Awesome. And come on up, my man. Last one, we know what it is. Central angle, where is it though? Where does it go? Where is the exact central angle? Very good. So what he's saying here is the central angle is this guy right here. This guy right here. Okay. Does that make sense, everybody? All right. Awesome. Now, let's learn some theorems today. Theorem 79 states that, very easy, guys, so don't stress it. If two angles of a circle, or of congruent circles, of course, are congruent, then their intercepted arcs are congruent, and that's what I was talking about earlier today, that some of you were questioning it. If two angles of a circle are congruent, then their intercepted arcs are congruent. So if angle QOP is congruent to angle ROS, then that means arc RS is congruent to arc QP. So if angle QOP is congruent to angle ROS, then arc QP is congruent to arc RS. Don't go by the drawing or how straight the line is or what you think it looks like. Go by the facts. And again, if ROS is X and QOP is X, that means RS is X and arc QP is X. And then that means that angle QOR is 180 minus X, and that means that POS is 180 minus X. And then that means that QR will also be congruent to arc PS. Does that make sense, everybody? Okay. And now, the converse. If two arcs of a circle are congruent, then their corresponding central angles are congruent. So in this case, it's the exact converse. If arc RS is congruent to arc QP, then angle ROS is congruent to angle QOP. So if arc QP is congruent to arc RS, then angle QOP is congruent to angle ROS. Does that make sense? Does that clarify a little bit what we were talking about before? Kind of? Okay, what, seriously, I want to make sure you understand this.
I'll show you later. So don't-
Okay, thank you, sir. Okay, next. Theorem 81. It's not hard. If two central angles of a circle are congruent, then their corresponding chords are congruent. And we proved this already before. Because you have the equal radii and you have the equal angles, so you have side angle side, and then you have congruent triangles, and you have CPC. But it's a theorem. So, and I'm sorry about that, I should have labeled this. Let's call this A, B, C, D, and E. So, according to theorem 81, if two central angles, ACB, being congruent to DCE, then chord AB will be congruent to chord DE. Yes, sir. And you prove this. How was the question? Well, this is a radii. This is a radii. That's congruent to that. This is a radii, and this is a radii of the same circle. So all the radii are congruent, so I have already side, side. But I have that this central angle is congruent to this central angle, so therefore, triangle ACB is congruent to DCE, therefore, AB is congruent to DE by CPCTC. But we don't have to go through all of that. We just got to remember and memorize the fact that if angle ACB is congruent to angle DCE, then chord AB will be congruent to chord DE. Converse is true as well. Okay, the converse is true as well. So if I have A, B, C, D, E. In this particular case now, if two chords of a circle are congruent, then their corresponding central angles are congruent. If AB is congruent to DE, then angle ACB is congruent to angle DCE. If chord AB is congruent to chord DE, then angle ACB is congruent to angle DCE. Does that make sense? Two more. We're almost done. Okay. If two arcs of a circle are congruent, then their corresponding chords are congruent. So if arc QP is congruent to arc RS, then chord QP is congruent to chord RS. So if QP is congruent to arc RS, then chord QP is congruent to chord RS. And its converse is valid as well. If two chords of a circle are congruent, then their corresponding arcs are congruent. If chord QP is congruent to chord RS, then arc QP is congruent to arc RS. Yes, sir. The question was, if you have one of them, you can prove all three of these theorems. Yes, sir, you can, sir. Thank you. Great question, my man. So if QP is congruent to segment RS, then arc QP is congruent to arc RS. Now, I know we're crunched for time here, and I really appreciate you bearing with me. Let me just go through these examples, and I'll make it right quick, okay? But I need you to know how to work this. I want you to find the measure of the minor arc here. Okay, 102 is right off the bat. Of course, this is the central angle, okay? The minor arc is AB, and central angle is equal to the measure of the intercepted arc, which in this case is the minor arc. So arc AB equals 102 degrees. Awesome, great, super. Just out of curiosity, though, I know I'm crunched for time, but if here, this angle here is 39, and I extended this, what would arc BC be? 78, because it's double. Great. Awesome. Okay, right quick. In this particular case, okay, I am given that you have circle O and D is the midpoint of AC. Okay, circle O and D is the midpoint of AC. Okay, all right, sorry about that. So circle B and D is the midpoint of AC. Okay, and I want to prove that BD bisects angle ABC. Okay? So, first off, I'm going to know that arc AD is congruent to arc DC. Why? AD is congruent to DC. It is not a given. It is the midpoint of an arc divides the arc into two congruent arcs. Of course. Definition of midpoint, guys. Okay. Next, angle ABD is congruent to angle DBC. Why? Thank you very much, son. If their two arcs are congruent, then the central arcs are congruent. Very good. Very good. And now from here, I can go ahead and define that BD bisects ABC. Why? Definition of angle bisector. If I bisected the arcs, then that means I had to bisect the angle. Right quick. Right quick. What fractional part of an arc is an arc of 36? Very good. So, 36 out of 360, it's going to be 1/10. What about of 200? 200 over 360, you're going to have 5/9 of the circle. Now, find the measure of an arc that is 7/12 of its circle. Well, you have 7/12 of means times 360. That's 30. That's 210. And we finished. Thank you very much. Have a great day. Great class.